deviations. Put them into variance. There's like this blockade here, so you put them into variances, add up that way, then go back down. Does that help?
Yes.
So we had kind of only done that with the normal stuff, maybe that's why I throw it off, but you can do it with any of it. So for the first part, you should have 2.87, I think this is 1.119. And then the variance, so that's the mean. That's standard deviation. And then the variance is just standard deviation squared. That was 1.25. Is that first part okay? Questions on anything there? Question on the third part too? Yeah, okay. What's Tom doing? So I've got a mean of 2.87 and a standard deviation of 1.119. And I've got another mean of 2.87 and a standard deviation of 1.119. Let's put them together to do distribution. Well, always Reagan. Oh, that's not fun. Reagan. I got you. Like if someone was talking about it, you want them to say like, oh, we'll just straight up
It means
Reagan.
like you're raking up the hits, like you're getting a bunch of hits.
Alright, so this one seems to be throwing people off, and because we had only done this with normal distributions so far, but it's the same idea. So I've got like a mean of 2.87, standard deviation of 1.119, and then I've got another mean of 2.87, standard deviation of 1.119. I want you to combine those. So the way you combine the means is you just add those two up, right? So that's 5.74. And then remember, you can't add up the standard deviations, so you got to put them both into variances. Well, this is the variance. So it's like 1.119 is here and here. What number is in is there and there? 1.25 is there and there, so what's the new variance? Is 2.5. And then I go, how do I go from variance to standard deviation? Square root it, and so that, I wrote that down. I lost it. What is it? Do people agree with that?
Yes.
Okay. Question on what I'm doing to get to it? Okay. This one's just reading up the chart, so less than 2.5 would be 1 and 2, so you're adding up those two as 0.35. And then this would be like if I add up, you know, I want to take one score and take another score, I want less than 8.5. So I wouldn't do, there's two ways to do this. One's a giant pain, one's less work. I could find, because these could add up to 2, 3, 4, 5, 6, 7, 8, 9, or 10, right? If I pick two and them together. So I could find 2, 3, 4, 5, 6, 7, 8. Those are all less than 8.5, but that's a heck of a lot of combinations. I think it's easier if you find 9 and 10, add up those two probabilities, and then do what? Subtract it from 1. So I'm going to find the probability that, I'm going to do this, 1 minus the probability that y is greater than 8.5. Because I don't want to go through 2, 3, 4, 5, 6, 7, 8. That's a giant number of combinations. So I'm going to subtract out the probability that's greater than 8.5, so 9 or 10. So I could get a 4 and then a 5. I could get a 5 and then a 4, or I could get a 5 and then a 5. And then if you do 1 minus all of that stuff, you'll get your answer. it's 0.9705. Anybody have that? Point what? So what'd you do differently than what I did here? Okay, so let's talk about that for a second before we move on to other questions. Is this continuous or discrete? Remember, continuous is like an infinite number of possibilities. Discrete is like there's countable options. So this is discrete, right? So you can't use normal CDF if it's discrete. So if that's what you did, that's why you're close but not like perfect. So if someone else did the same thing, so that's why. So it doesn't say normal. You only use normal CDF if it says normal. Any other questions, comments? Again?
For the 5 and 5 needs to do it twice.
No. Okay. So if you think about like a tree, you know, your first score is 1, 2, 3, 4, 5, and then there'd be 5 coming off that, and the only way to get to 5, 5 is like that one. Does that make sense?
Yeah.
Other questions here? So there's one more kind of. So that's reviewing the discrete stuff. This is reviewing more of the normal stuff. So I'll give you a couple minutes on those, and then we'll go through those, and then we'll get the new material. Yeah. I mean, if you choose to do it, I don't know. He did his work. Yeah, you're trying to do your work. That's what it is. You do your work in class. That's true. That is true. So that's the first one. If you're stuck, you know, maybe that'll help you kind of remember what you're doing. So I want less than 210, so negative 999 up to 210. How did I get this 200 number? The 102 plus 98, right? How did I get this 17.7 was the Pythagorean theorem thing, right? So 13 squared plus 12 squared and then the square root. How many already had that? 0.714. Nice. choice, but just a good habit. So I got 0.362 for that one. Is that what you just said, Mike? Oh. Did you get that though? Do you know either? Okay. 0.386 the last one. Everybody get that?
Yeah.
Alright. So I'll wait a second because I know not everyone's done, but there's your answers, there's the work.
That was great.
What's up? You're right? You're right?
Yeah. I'm gonna try it for one. I put 0.614.
You did less than.
So if I can read
I'll show you where if needed. Questions on these three? Anything I can go over? Review, refresh? Anything here? Alright, so there's really three things that are going to be on this test. One is like the first problem we did, so the discrete stuff, where it's like 1, 2, 3, 4, and I'll ask you a bunch of questions about that. 2 is where it's combining normal distributions, so something like this. And then 3 is expected value, which we're going to do today. So that after today we've done all three things. We'll review, do frappies, etc. New test should be Thursday. Yeah, well, it's short topics, but it doesn't mean the test will be shorter. You know what I mean? There could just be more questions on each topic.
What if this is the type where you decide to make a really long test?
Oh yeah, I'm still mad at you for finishing my test so fast though. So this is gonna be like 80 questions. Yeah, Michael saved you guys. Someone used all their time. If everyone had been done 20 minutes, I'd been more mad. I'm not really mad. I'm just messing. All right. Right. So there's two sides of this worksheet. They look extremely similar. So make sure you're on the same side that I am. Just the numbers are different. Basically, I'm going to do one.
The one that's bolded.
Yeah, do the one that's bolded first. All I did was, like, we're going to do these 5 problems. I change the numbers, put on the back, and then you'll do that. So I'm going to go through, like, one of each type, you know, and then give you a chance to practice one of each type. So expected value is the same thing as mean. It's just another phrase for mean. So if I were going to do number 1, there's a couple ways I could do it. One way you could do it would be set up a table, same way we just did on the warm-up. And go, okay, x, p of x. So x is going to be, in this case, the money I win. So I could win $200. What's the probability that happens? 1% of the time, so 0.01. I could win $50. That happens 10% of the time, so 0.1. the rest of the time I win nothing, which would be, 0.89. Where am I getting the 0.89 from? Because those all have to add up to 1. So your job is to find the expected value, which is the same thing as the mean. So could you put this in your L1 and this in your L2 and have your calculator find it? Yeah, that's absolutely fine. That's one way to do it. Another way, kind of a shorter way, and what your calculator is doing is you're just multiplying each of these together. So it's the outcome times the probability of that outcome, plus, that actually looks like a giant plus sign. The next outcome times the probability of that outcome, plus the next outcome times the probability of that outcome. So you'd go 200 times 0.01, plus the next pair, plus 50 times 0.1, plus 0 times 0.89. So, is that $7?
Yeah.
So you can do it either way. This takes a little longer because you got to throw it in your calculator, but it's like it's not going to screw up the math, This is a little faster, but you got to make sure you do the math right. And then I want to talk about expected value for a second. Is it possible to play this game and win $7? Well, then how is my expected value 7? Like, where's that coming from? What's that mean? What? Well, my total outcome could never be 7. My options are 250 and 0, so what's the 7 mean?
That means like if you played enough times, you made about $7 every time you played.
This would mean if I played it, like, for infinity, took all my outcomes and divided it by the number of times I played, it averaged out to $7. You don't want to play a game where you average getting $7 every time?
Well, if it costs $10.
Well, that's the thing. Okay, so if you paid, would you pay $6 to play this game? That's up to you. I would.
I would play it enough times until
If I could pay,
eventually I'll get higher.
if I could pay $6 to play this game, I would play it as many times as I could. Because on average, over the long run, I'm going to win $1 every time I play. I can't win $1 any specific time, but on average, I'm going to win $7 every time, and I'm going to lose $6. So that comes out to a +1 for me. So okay, you walk into a casino and they're like, "Here, enter this drawing. This is casino. This is how casinos are billionaires." You see this, and they charge you $8 to play. Mathematically, should you pay $8? You should not. Will people pay $8?
Absolutely.
Absolutely. And so every time that someone pays $8, how much does the casino theoretically win? $1. Every time someone enters, they win $1. In theory. It doesn't really add up or like even out for a really long time. So you could walk in, play once, and could you walk out with $200? Yeah. But if you play it forever and ever and you're spending $8 every time, you might as well just throw the money at the casino. Here's another instance. So I'm not going to do this problem, but have you guys seen, what is it, Deal or No Deal? So you got the briefcases, So yeah, it's Howie Mandel. So let's say they get down to, let's say 3 briefcases. One of them's $1. One of them is $50. One of them's $1 million. First, I want you to find the expected value. So do the same thing we just did for number 1. Find the expected value for that. I don't know if you haven't seen the game. Basically, you've got a 1 in 3 shot of getting any of those. And then you can choose to continue and guess, or you can choose to just take the bank's offer. But let's find the expected value first. We used to, if it weren't right up against spring break, we'd have time. We'd take a class and play Deal or No Deal. Or not spring break, but whatever. But we don't have time right now, unfortunately. So what's the expected value? EV or X bar, expected value or the mean. 333,000. $350. 33 cents. Should I go through how I'm getting that? We're doing 1/3 times 1, plus 1/3 times 50, plus 1/3 times a million. So if you did 0.3, so that's not going to quite, it's just going to be a little, because you only ended up to 0.99 instead of 1, so you're probably a little short.
Yeah.
So what the bank will do, and so they'll come in with this offer, they'll say, we're going to offer you, are they going to offer you that much? They're not going to. They're going to offer you, they'll say, here's your offer, $225,000. We'll play a little mini version here. How many of you are going to walk away? We're all down to 3 briefcases. You're all going to play your own individual game. How many of you are going to walk away with that $225,000?
100. I would totally do that.
So, if you could play this game 1 billion times, would you walk away?
No.
No, but you can't, right? It's a different story because that's like life-changing money. So, I mean, for most of us, for me it is. So yeah, I can totally understand why you would not do like the mathematically correct thing because you don't get to play it over and over again. All right, so if you just raised your hand, you're out. You're done. All right. I have one in my head where the how's this gonna work? Close the briefcases. I know.
Just pick a random number for each. Yeah, put 1 through 3 in a random number.
Yeah, I'll do random number 1 through 3, and whichever one the calculator says gets eliminated.
Yeah.
You do random int 3, so it told me. It told me 3. If you stay in the game, your options now are $50 or $1. Find the expected value. Find the expected value. Tough lesson right there. What's the expected value now?
$25.
It's not even real money, but I still think about it.
So, your offer now is $23. How many of you that were still playing are going to take the $23?
I wouldn't. The thing is, like nothing a lot.
Right.
It wasn't just fair,
Okay.
fair values.
Let's see.
What do you do?
I'll show you later. 50 just got eliminated. If you stayed in the game, you ended up with $1.
Okay, you did that.
I didn't. I'll show you. I'll prove it. I don't care about the game, like the results. Do you understand, like how I'm figuring out the expected value? Okay. All right. Let's look at number 2. You're just dividing by like 3 or 4. It's not that hard.
Well, darts are like, doesn't it start off with like 15 boxes though?
Yeah, but no one's stopping that early.
I don't know how you.
The offers are more fair early. When there's like a huge discrepancy like that, then they know they can slide the offer down. All right, read that second one. Read the second one. So there's a couple ways to set this up, and I want to talk through both. Some people just think about it like each way. Some people will kind of put that $3 that you paid into every outcome, and some people will forget all about the $3, figure out the expected value, and then subtract 3 at the end. So you can either distribute 3 as you go, or like wait till the very end and get rid of the 3. So if you're thinking about the 3 as you go, you didn't really win $10 here. How much did you win? You won 7, 1/4 at the time. this isn't really 5, it's really 2, 1/4 of the time. If you get your money back, now where are you at? 0. And then this one, if you paid $3 and now you got to give another 5, now where are we at? Now we're at -8. Other people think about it this way. Well, I could have won 10, I could have won 5, I could have won 3, or I could have lost 5. And then after all of that, they'll be like, okay, -3 equals. Because no matter what, I had to pay that $3. So that -3 either goes to the very end or it kind of goes into each outcome. Does that make sense, the difference? You can do whichever one you want, but go ahead and find the expected value there. That's 25 cents.
Yeah.
So if I figure this out, it's 0.25. If I figure this out, what is it? 3.25. Then you pay the $3, so it still ends up with 0.25. So would you play that game if you were offered a chance to play it for free? Yeah. I mean, you might lose, but if you play it a bunch of times, you're going to theoretically collect a quarter every time. But then you go to the casino and they charge you 30 cents to play this game. Oh yeah, the $3 is weird. Anyway, do you understand what I'm doing to get the answer? Okay. Try number 3. 0.25 is right.
Electric does have a lot of statistics.
Blackjack is the goods for the casino, not for you. Oh. Here.
Well, that's because playing blackjack is so terrible. There's reasons to play that.
So the expected outcome if you play 20 games is you just take the expected outcome of one game and then just multiply it by 20. We're just
Like
gonna
on
run
the
a
surface,
casino.
you-
Right?
What?
We're just gonna run a casino.
Yeah. Because like on the surface, it actually seems reasonable until you run the numbers, and it's not. So.
I mean, just the general idea of why would they run it if it were reasonable? You know?
Yeah.
So you get -75 cents for one game, and then you would do -0.75 times 20, and you would be, if you played 20 games, you'd be expected to lose $15. Now, could you walk into the casino, play 20 games, and come out ahead?
Yeah.
Yeah, and that's why casinos exist, because people think they can do that. But if you play it over and over and over, unless you're counting cards or doing something kind of illegal, you're going to lose. Try 4.
Yeah, they generally put like 6 decks.
Yeah, there's like 6 decks of cards, and so there's, that's 312 cards you got to keep track of, and they fly. Let's try 4. 5 is pretty tough. We'll do that together, but I think 4 you're okay with. So if you won half the time and the casino won half the time, it'd be a totally fair game. You could expect to play forever and come out pretty much even. But it's not 50-50. There's slightly more options for them. Which is how they make their money.
But if everyone played reasonably, they wouldn't be out too much for that.
Well,
I mean, if it was set up like that.
that is how it's set up.
Somebody plays 20 times and loses $15 overall.
So if you want to look at that as like the cost of your entertainment,
Yeah.
you know, that's how some people view it.
It's not always true. And then 30,
Yeah.
and then 5. I mean, absolutely.
Yeah, and then people start losing and they're like double their best to try to catch up.
Yeah.
So you get negative 0.526. Yeah, so it's negative 53 cents on average every time you play. I mean, you can walk into a casino, you can look at the wheel and be like, well, they're going to win more than half the time, I'm going to win less. And I'm still going to play. Kind of boggles my mind, but that's the way to do it. Well, then people do this too, like, well, it's been green the last 4 times. And then some people will be like, so it must be green next time. And some people will be like, well, red is due. But do the last 4 have anything to do with the next one? Not at all. So people try to play streaks. I'm going to give you a chance to try 5 because we have time to give you a second on it. And then if it, I'll go through it too, but try it, see what you can come up with. Yeah, but you got stocks.
60% of the time for $20 pretty good.
Just go to the first doctor 3 times for 20.
That's a good point.
If he has a 60%.
So now you're at 84% for $40.
Anyway, I didn't even finish reading it. Think about it like this. If you go to the first one, but you be sitting with it, I expect a little bit more time. Look, if you go to the first, you need this, you have to. It doesn't say you're in the
this game, yeah.
But you could just spend $60. The game.
In your way, even if you keep going to the first doctor, you never guaranteed.
Yeah, you never guarantee your chance of winning.
Yes.
So you save money.
Try it.
Anyway.
So here's the thing with this one, and this is where people mess it up. If you're making a little chart, or I'll do it the other way too, but you could spend $20 60% of the time, right? What percent goes here where you have to go see the second doctor? 0.4. If you have to go see the second doctor, how much money did you spend? It's not 60. It's 80. Because you had to pay for both. So your expected cost, well, there's a 60% chance that you're done after the $20. But then if that didn't work, you have to go see the second one, which happens 40% of the time. And then you've ended up, you paid for both. So if you're doing it the other way, it'd be 0.6 times 20 plus 0.4 times 80. So that's 32. So that's $44. With that strategy, and the other strategy would be like, I'm just going to straight up go with the second one. But that costs 100. So this is actually going to save you money over the long run, but then it's like, okay, do I want to go to 2 doctors? Do I, there's a time issue too. But does that make sense how I'm calculating the 44? Your homework is to do the problems on the back.
I'm not going to tell my if I haven't done one.
That is a downfall in my...
No incentive to live.
Yeah.
No incentive to live. Well, if you have
6.4 chance, percent chance of not being cured if you went to the first one 3 times.
So that's 0.4 to the third, and 1 minus that? Yeah.